My parents grew up with steam shovels, excavators that dug sewers, cleared land, and were used in many forms of construction. Steam-powered excavators soon gave way to diesel-powered ones. Mechanical things at the time were typified by levers, gears, and steel cables. All that has changed, for today it's hydraulics, with pistons replacing gears and levers. Hydraulics is the study of fluids under pressure, which nicely employs Pascal's principle, the underbelly of today's machines, from playful gadgets to skyscraper cranes. So what is Pascal's principle? It's simply this. A change of pressure at any point in an enclosed fluid at rest is transmitted undiminished to all points in the fluid. You know you can exert a force on a faraway object if you poke it with a long enough stick. What Pascal tells us is that you can do the same with fluid in a pipe. Every time you step on the brakes of a car, for example, you're employing Pascal's principle. The force you apply to your brakes produces pressure in a fluid that is transmitted to the brake drums in the car's wheels. Fill a U-tube with water and place pistons at each end. Apply pressure to the left piston and it will be transmitted throughout the liquid and against the bottom of the right piston. The pistons are simply plugs that can slide freely but snugly inside the tube. The pressure that the left piston exerts on the water will be exactly equal to the pressure the water exerts against the right piston. It's easy to imagine if you push down on the left piston, the right piston goes up. This is nothing to write home about, no big deal. But suppose you make the tube on the right side wider and use a piston of larger area. The result can be impressive. If the piston on the right has 50 times the area of the piston on the left, you can multiply your input force by 50. That's right, with no levers, pulleys, or gears. Here's where the distinction between force and pressure comes in. Recall that pressure is force per area. Turn this around and you get force equals pressure times area. So whatever pressure you impart to the left piston will be imparted to the right piston. That's not the impressive part. What is impressive is force. Whatever force you apply to the left piston, 50 times more force can be exerted by the right piston. This arrangement of pistons can multiply force. Yum stuff? For example, place a 10-kilogram block on the left piston. How many kilograms will the right piston support? Did you say 50 times as much? 500 kilograms? Correct. This is something to write home about. This is a big deal. Here we see Pascal at work in a service station. There's only one piston here. And we have two types of fluid, air and oil. The air compressor pumps air into the reservoir. This pressure is transmitted through the oil all the way to the bottom of the piston that supports the car. How much pressure is needed to hold the car aloft? Pressure is force over area. The force would be the weight of the car and the rack it sits on. A reasonable figure for this is 3,000 pounds. A reasonable area for the piston is 200 square inches. So the pressure, 3,000 pounds, over 200 square inches is 15 pounds per square inch. 15 psi, about the same as atmospheric pressure. So an additional 1 atmospheric pressure, easily supplied by the pump, can lift the car. Said another way, a gauge pressure of 1 atmosphere can lift the car. Gauge pressure is over and above atmospheric pressure. When a tire is flat, for example, its gauge pressure is 0, but there's still atmospheric pressure in it. Gauge pressure, what gauges read, is the pressure in addition to the ever-present atmospheric pressure. The popularity of Pascal's principle is apparent everywhere. Here's a modern excavator with its pistons. Here we see 2 hydraulic pistons at work lifting this dumpster. Here's a large crane. Note the hoses that transmit the hydraulic fluid under pressure to the large piston. And here's an interesting situation where piston sizes are reversed. Do you think the fellow will be successful in exerting enough force on his piston to lift the 10-kilogram mass on the other end? Do you know why? I don't think so. I want to conclude with this information. Pascal's principle can multiply or diminish forces, but no set of tubes and pistons can multiply energy. So here's my concluding question. As we've seen, with a proper piston arrangement, you can certainly multiply input force. Why won't this piston arrangement similarly multiply energy? What's your explanation? Until next time, good energy.